Let's have a look now at trigonometric ratios for angles other than acute angles. And we're going to start off with the obtuse angles. So if you've hopefully watched the last video, now the last video was about the unit circle drawn on a number plane, and also looking at how angles are measured on a number plane as well. Okay, so just a quick recap, angles are always measured from the positive x-axis and measured anti-clockwise. Okay, so think of it as the sun rising from the east. At midday, the sun's almost 90 degrees ahead. Well, that's if you're on the equator and sort of at the equinox. Of course, the sun will be 90 degrees straight up, or as high as it's going to get. And then the sun sets in the west, and sort of there's night time down here, and we'll deal with that later. But the focus of this video is just the obtuse angles for now. We also know that this first quadrant here, so the quadrant basically from the bordered by the positive x-axis and the positive y-axis here. So this is the sort of the northeast quadrant. It's called Quadrant I, and they involve angles between 0 and 90 degrees. 0 degrees, okay, is the positive x-axis, and we're measuring anti-clockwise. So 90 degrees is the positive y-axis. In fact, I might just put a plus sign here so we know it's a positive y-axis, and this is the positive x-axis down here. Now I've drawn in part of a unit circle. Okay, it's a unit circle because it has a radius of 1 and it's centered on the origin there. So in other words, any line drawn from the origin to anywhere on the circumference of this circle will have a length of 1. That's its radius. Okay. That means then that I could draw a radius and then complete a right angle triangle. And I think this is at the point where I could say that circles meet triangles, and especially right angle triangles, and trigonometry, in fact, has its origins around basically inside a circle. In fact, so it's funny how we learn trigonometry by just looking at right angle triangles, but the origins of trigonometry, in fact, reside in a circle. In fact, you sort of can't do one without the other. And in fact, you're looking at the real trigonometry now. So this is the trigonometry that's involved with circles as well. Okay. So the hypotenuse of a right angle triangle happens to correspond with the radius of that circle, of this particular circle, or of any circle that it's drawn inside. All right, moving on. Let's focus on Quadrant I for a moment there. Okay, so there's a point P. It's on the circumference. The hypotenuse is 1 unit because it's inside this unit circle. In other words, the radius drawn from there to there is 1 unit. All right, so it doesn't matter where I put point P. I could put it anywhere I like. Doesn't really matter. Okay, the hypotenuse is always 1. So and in the first quadrant, okay, the positive x-axis, well, that's positive. So this side here of the triangle, okay, so this horizontal short side is positive. This vertical short side is positive because it's above the x-axis, okay? So anything to the right of the origin is positive. Anything above the x-axis, so this is the y values, are also positive. So that's why I put positive signs here. So plus, and the hypotenuse, of course, it's going to be positive. Firstly, because it's the radius of a circle. And secondly, because of Pythagoras' theorem, if you take whether they're positive or negative numbers and you square them, you're going to get positives, okay? You take the square root of a positive, you get a positive number. So you end up with a positive hypotenuse, okay? The other thing as well that's worth noting is the coordinates here. What are the coordinates of point P, x, comma, y? If we have a triangle here, okay? So I might just redraw the triangle here. So just going to sketch it quickly, okay? So there's our triangle. There's our angle theta. Sorry, it's not the neatest triangle, but okay. Now, call this x, okay? So this is this length here, okay? Is this length here. This vertical short side is y, all right? And there's our point P. Now, the hypotenuse is 1 unit, okay? Let's have a look at the cosine and the sine of theta in this particular triangle, all right? So cos of theta, okay, is equal to adjacent over hypotenuse. X over 1. X over 1 is just x. Sine of theta is equal to opposite over hypotenuse. That's why we use a unit circle. You might think, what's the significance of this unit circle? Why use it? Because 1 is a very convenient number. And when you divide by 1, nothing changes. It's kind of very nice. We try to pick nice numbers in maths, don't we? Yeah, we could pick any circle. It doesn't have to be a unit circle, but yeah, well, let's pick whatever's easiest. Y over 1. Y over the hypotenuse of 1, and that's equal to y. So these are our coordinates, aren't they? Right? So in other words, instead of writing x comma y here, I could write cos of theta, comma, sine of theta. Right? How cool is that? I think that's just awesome, right? In other words, instead of just having x comma y, as long as you give me an angle, all right, and you tell me how far from the origin I travel, I could land anywhere I want on this unit circle, or anywhere for that matter, in fact, on any circle that I like, or anywhere on this number plane, okay? So that's sort of another way that we can actually use coordinates, in fact. So these are what we call polar coordinates. You don't have to worry too much about why it's called that, but it's something to do with circles, of course. Okay, but I might just make a point of this. So this y is really sine theta, okay? And this x coordinate is really cos theta. All I need now is theta. And then I've got the coordinates of point P. As we sort of move around the circle, obviously these coordinates are going to change. So let's say, for example, theta was 30 degrees. What would the x coordinate be? Let's try that. Cos of 30. Okay. Well, we know what that is. That's just root 3 on 2. So in actual fact, x would be at root 3 on 2. So roughly around 0.866 to the right of the origin. What about the y value? Okay, so the y coordinate, that's going to be sine of 30. 1/2. So it's in fact 1/2 of the way up, isn't it? I've drawn this roughly to scale such that the theta is around the 30-degree mark. You can see that it's almost halfway along, isn't it? So if you sort of go across there, there's about half there, right, all the way across. It's halfway up to 1. So it's about right, isn't it? Okay, so I just wanted to just sort of talk about that, where these coordinates come from. Now, the next thing that we're going to talk about now is the ratios in these two quadrants and how they differ, and sort of to answer those fundamental questions. Like, y is sine of 150, positive half, but yet cos of 120 degrees is negative half, and tan of 135 degrees is negative 1. Where does the negative come from? All right, so angles in quadrant 1 are acute, 0 to 90 degrees. These are just your regular triangles, okay? So nothing changes here. In fact, every triangle that you've looked at since you've first looked at trigonometry, doesn't matter how the triangle is drawn, it's kind of like assumed that the triangle is actually, in fact, it's actually located in quadrant 1. You've been doing quadrant 1 triangles all your life, okay? Up until almost to this moment, okay? Now what I'm going to say to you is, if we've located this triangle here, okay, so this triangle in quadrant 1 originally, and we flip this triangle around to quadrant 2. So just imagine we did this, kind of like flipping a pancake or something, right? So do this and go whoop, and just flip it around. You've got the exact same triangle, okay, congruent in other words. So in other words, the angle inside the triangle is in fact identical. So that's theta in fact. Okay. So what I've done is I've just copied the same triangle, but just flipped it around. There's your theta. Okay, so that theta is exactly the same as this theta here. Okay. Okay, I might call this, instead of point P, I'm going to call this point Q. Okay. Right, and it's going to have slightly different coordinates, of course. Okay, but this is quadrant 2 now. So quadrant 2, these are your obtuse. Okay, and these are your angles from 90 to 180 degrees. So let's see what happens now. Now, in quadrant 2, so what we've done now, we've flipped the triangle around, but now we are referencing the lengths of this triangle, or in terms of the short sides. Okay, so the horizontal short side and the vertical short side, we're now measuring those relative to the origin. So relative to the origin, we're going now to the left-hand side. So what can you tell me then about this horizontal short side? Is it positive or negative when you are referencing or relative to this point here in the middle? What do you know about number lines? Points to the right are positive. Points to the left are negative. Big negative there. Okay? Points above the x-axis. So the y-axis is really just a vertical number line. Anything above the origin is positive, big plus. Okay? The hypotenuse, okay, because it's the radius of a circle. Okay? Forget Pythagoras' theorem for a moment. This is really the radius of a circle. It happens to be the hypotenuse of this triangle as well. Okay? So because it's the radius of a circle, you don't have negative radii. The radius is just the distance from the center to anywhere on the edge. And you and I know that that's always going to be a positive number. A negative radius doesn't make any sense anyway, at least in this context. Now, if you want to then use Pythagoras' theorem to prove this particular point, take a negative side squared, positive side squared. A negative squared is positive, right? So negative squared plus positive squared still gives you a positive number anyway. You take the square root of that, you get a positive hypotenuse. So the hypotenuse is always going to be positive. So let's see what's happening now to sine, cos, and tan. First of all, let's have a look at quadrant 1. I might use a slightly different color here just to differentiate this the two quadrants. All right, sine theta is going to be positive in this quadrant. Cos of theta will also be positive, and tan of theta is also positive because all the sides, they're positive, they're actually positive numbers. In dividing them by each other, because they're a ratio of sort of two sides, sine is opposite over hypotenuse. Okay, so opposite over hypotenuse, plus divided by plus gives you a plus. Cosine, all right, it's a positive adjacent side divided by a hypotenuse, which is positive. Positive divided by positive gives you a positive. The tangent ratio, okay, opposite over adjacent, or sine divided by cos, whichever way you want to look at it. Plus divided by plus gives you a plus. So in quadrant 1, all trig ratios are positive. Let's now compare that and contrast that with quadrant 2. Okay, so with quadrant 2, we have a negative adjacent side, a positive opposite side, and a positive hypotenuse. But there's one little thing that I haven't talked about yet. When we measure this angle, or we measure the angle of this line here, OQ, okay, so from the origin to point Q, it's incorrect to measure the angle from the negative x-axis. This is wrong. Can't do that. Not allowed. Oh, where do we measure angles from? All right, and toward the beginning or toward the early part of this video, angles are always measured from the positive x-axis. Okay, so I'm kind of stressing this, and I've stressed this a few times. We've got to measure the angle this way. Now, this is in fact the angle, 180 degrees, minus theta. After all, they're supplementary, aren't they? They're on a straight line. Okay, if this happens to be our angle, our acute angle theta, the angle that we in fact use is the angle measured from the positive x-axis, measured anti-clockwise. Again, it's like bearings. Everything has to be measured from some reference point or reference line. The reference line here is the positive x-axis always. Okay, so we need to make sure we really sort of drum that in, okay, and etch that in stone. Okay, so this angle here is in fact obtuse. So there's our obtuse angle. Okay, so if theta happens to be 30 degrees here, what must this angle here be? It'll be 180 degrees minus 30. This will be 150 degrees. Okay, so in fact, just to sort of highlight this example, I might just quickly draw that. So if that was 30 degrees, okay, this happens to be 30 degrees here as well, but we can't measure an angle backwards from the negative x-axis, so it's sort of in the clockwise. In fact, we have to measure the angle that way. So the correct angle, in fact, or the correct way to measure this angle is in fact 180 degrees minus 30. That's 150 degrees. Okay, and that's why one of the questions I asked at the start of the video, why is sine 150 degrees 1/2 or positive 1/2? And we're getting very close to that answer. All right, let's have a look at the sine, cos, and tan ratios in quadrant 2. Now, sine of theta, okay, opposite over hypotenuse, plus over plus, which is positive. Okay. Cos of theta. Okay, in this case. So when we use theta, we're not using the acute, we're using the obtuse theta. Okay, but regardless, let's just bear with me for a moment. Cos of theta, okay, is adjacent over hypotenuse, negative over a positive, which gives you a negative. Tan of theta, okay, is opposite over adjacent. It's plus over minus, and that gives you a minus. So only sine is positive in quadrant 2. Okay. Sine is positive in quadrant 2. Cosine and tan and tangent are negative in quadrant 2. Okay. So I'll just summarize that on this side here. Then we might look at some examples. Okay. So in quadrant 2, okay, sine of theta is positive. Cos of theta is negative. Tan of theta is negative. Okay, so you might have heard of I guess the all ubiquitous all stations to central. We'll talk about that in another video where I just quickly summarize all of this hopefully in a few minutes. Okay, but there's your all and there's your stations. Right. So if you're given an acute angle theta, what's the obtuse angle? So let's say if theta happens to be, for example, 30 degrees, okay, then theta obtuse is equal to 180 degrees minus 30, okay, which equals 150 degrees, okay, and that's the relationship between the two. So given the acute angle, we find the obtuse angle by subtracting the acute angle from 180 degrees, and we get the obtuse angle from that. All right, and that's actually the reason, one of the reasons why, for example, if you put in sine of 30 degrees, you get half, and if you put in sine of 150 degrees, you also get half as well. Okay, because they're basically the same triangle, and it just so happens that the opposite sides are, in fact, at least in this case, are identical to each other. So this side here is positive, this side here is positive, the hypotenuses are the same, so it stands to reason then that the ratio, the sine ratio in quadrant 1 and quadrant 2, the sine ratios are identical to each other. Okay, all right, let's have a look at a few examples, and then we'll in the next video I'll be having a look at trigonometric ratios for reflex angles. Here are 4 examples. Okay, so we'll just have a quick look at these. Okay, so find the value of the trigonometric ratios for the obtuse angle given the acute angle. Okay, so I've given you the trig ratios as acute angles, but we want the ratio for the angle obtuse. Okay, so first one, sine of 30. Okay, I think we know what this one's going to be. Okay, so for the obtuse angle, okay, what we want is sine of 180 degrees minus 30. Okay, that's equal to sine of 150 degrees. Okay, and in fact that's equal to 1/2. That one we've seen already. Okay. Okay, what about cos of 60 degrees? Okay, for the obtuse angle, okay, that's cos of 180 degrees minus 60 degrees. That's equal to cos of 120. Okay, and we know that cosine, okay, is negative in quadrant 2. Okay, so this is a quadrant 2 angle, okay, it's negative, okay, which is actually negative cos of 60 degrees, okay, which is in fact negative root 3 on 2, or negative 0.866, depending on how many decimal places. So root 3 divided by 2, and you can put in 3 decimal places negative 0.866. 0.866, okay, to 3 decimal places. Okay, what about tan of 45? Its obtuse angle, okay, is tan of 180 degrees minus 45. Okay, that's equal to tan of 135 degrees. Okay, and this is also quadrant 2. Okay, and it's actually quadrant 2 negative. Okay, so remember that angles in quadrant 2, okay, or trigonometric ratios for angles in quadrant 2, okay, sine is positive, cos is negative, tan is negative. Okay, so that's really the same as negative tan of 45, which is negative 1. Okay, so again, we've done this in the beginning. Tan of 135 is negative 1, which is really the same as negative tan of 45 degrees, which is negative 1. Last one, sine of 20. Okay, that's equal to, okay, so if you want the obtuse angle, okay, so that's 180 degrees minus 20, okay, which is equal to sine of 160 degrees, but this is quadrant 2 positive, okay, so sine is positive in quadrant 2, so it's in fact the same as sine of 20, in fact. So if I do sine of 20 degrees, okay, 0.342, okay, sine of 160 degrees, it's also 0.342, okay. Correct to 3 decimal places.